Hi, my name is Will. I'll be joining the Material Science faculty next April. Unfortunately, I'm not there to chat with you, but if you have any questions about what it will be like to work in my group or the research that we'll be doing, feel free to reach out to me over the internet or by phone. My past work has focused on application of transmission electron microscopy, or TEM, to the study of ceramic materials used in electrochemical energy conversion and storage devices like batteries and fuel cells. For information about my publications, please visit Google Scholar or ResearchGate, or the website of my current supervisor, Professor Bilge Yildiz. I research materials called non-stoichiometric oxides, whose useful properties, such as electrical conductivity and catalytic activity, originate from their ability to exchange ions with their surroundings. For example, cerium dioxide exchanges lattice oxygen with gaseous oxygen by a reduction-oxidation reaction. Using the TEM, we can directly image this process, which causes atomic rearrangement at the surface of this nanocrystal during oxygen exchange. To form bulk ceramics, these nanoparticles can be heated to form a huge range of morphologies and compositions. Here, you can observe late-stage sintering of an oxide at 1200 degrees Celsius using in situ environmental scanning electron microscopy. In the past, I've worked extensively on characterizing electrical and chemical properties of grain boundaries in polycrystalline materials, which are found throughout materials science and engineering. Dense and porous polycrystalline ceramics comprise many electrochemical devices like batteries, sensors, separation membranes, next-generation digital logic and memory devices, fuel cells, and electrolyzers, which all contain multiple oxide phases. Typical device architectures include the electrodes, where chemical reactions produce and consume electrons, and an electrolyte separator, which is a dense polycrystalline phase whose performance typically depends on how quickly ions can diffuse between the electrodes. If you are interested in reading about my work in these areas, I encourage you to find my publications on oxygen electrolytes, oxide thin films, resistive switching memory devices, and solid-state lithium-ion batteries. Information about this work is available on Google Scholar and ResearchGate. I also keep an approximately current CV on my personal website. My work aims to study and develop materials by applying advanced electron microscopy and spectroscopy methods. I focus on materials for sustainable energy conversion and storage applications, and catalysts for chemical fuel production. I aim to design these materials over many length scales, from the device scale down to the atomic level. And I apply a holistic approach to materials exploration and design, including synthesis, performance testing, and characterization. I plan to initiate several projects with my first students, but I'm only able to highlight 2 today. You may be familiar with videos like this of an electric vehicle battery on fire, or images like this of a device destroyed by combustion of a battery's liquid electrolyte. These events have fueled a lot of interest in developing all solid-state lithium-ion batteries, which replace the liquid electrolyte with a solid. Numerous labs and firms are exploring ceramic electrolytes, and the field is still relatively open for new and innovative strategies to improve device components and performance. Solid electrolytes enable higher theoretical energy density due to their chemical stability against lithium metal. These batteries are not without flaws, however. Because the electrolytes are solids, lithium-ion conductivity drops with temperature, thanks in part to highly resistive grain boundaries, which degrade ion transport in many similar solid electrolytes. Grain boundaries can also become plated with lithium metal during battery operation, causing batteries to fail by short circuit. I plan to develop design strategies to address the dual issues of poor lithium conductivity of grain boundaries and lithium metal plating. This will be done by exploring and designing the synthesis processing performance relationship based on new multiscale characterization approaches centered around TEM. The second project is on a new type of oxide-embedded metal catalyst for oxygen electrodes in electrochemical cells for energy conversion and fuel production. These cells, like the hydrogen fuel cell, which emits only steam, generate electricity by chemically converting fuel molecules. Many of these cells must reduce molecular oxygen to ions via the oxygen reduction reaction, which is still under investigation in academia and industry. Recently, it was shown that several oxygen reduction catalysts undergo the process of metal exsolution, where metal cations diffuse to the oxide's surface to form anchored catalytic nanoparticles. These anchored nanoparticles have superior durability without sacrificing activity at service temperatures. However, the exsolution mechanism is unclear, and new exsolution-compatible compositions are regularly reported, so room exists to develop optimized catalysts. To design better exsolution catalysts, I plan to track exsolution in real time using in situ TEM. These systems have complex morphologies with metal nanoparticles embedded in polycrystalline oxides. I plan to observe the exsolution process with high frame rate electron imaging cameras and use these mechanistic insights to improve processing and to find new routes to control exsolution through defect engineering, for example. It is very exciting to see what these modern electron cameras can observe, like the atomic motion at this nanoparticle's surface. To process big video data sets produced in the electron microscope, and to automate laborious data acquisition, I'll utilize deep learning algorithms for motion capture and computer vision. Here, researchers have tracked the body parts of this fruit fly and the parts of this rodent's hand using motion capture. In material science, deep learning algorithms have already interpreted complex, experimental, atomic scale microscopy data and complicated material microstructures with accuracy comparable to human researchers. This example comparing human and computer image interpretation is from Carnegie Mellon University professor Elizabeth Holm, with whom I've discussed my proposed research and who is interested in collaborating with me on this work. My long-term goal here is to develop an algorithm to first track the motion of nanostructural features during real-time exsolution to allow derivation of kinetics from in situ data. Eventually, I will apply this approach to other complex dynamic processes like sintering, grain boundary motion, particle coarsening, and chemical absorption and desorption processes. The ability to track material motion down to the nano and the atomic scale is not only visually exciting, but it is also extremely scientifically valuable. Developing and improving theoretical models relies on such novel datasets which capture the actual nature of atomic and molecular dynamics. In this vein, I am currently working on a funding proposal with a fellow MIT postdoc and incoming UCI assistant professor in mechanical engineering, Pengwei Chao, who is an expert in molecular dynamics of metal nanoparticles and materials interfaces, and we are both very excited to get this collaborative work off the ground. I intend to develop state-of-the-art materials using synthesis and fabrication routes guided by correlated electrochemical and electron microscopy characterization. As a group member, you will be able to do material synthesis, performance testing, and characterization. By following the material from synthesis through testing and characterization, you will gain a deep understanding of the nature of your materials. You will be able to make your own materials, either by synthesizing ceramic nanoparticles by wet chemical methods, like propellant-driven synthesis, as you can see here, or by other fabrication methods in the lab. Here, cation precursors are dissolved in a flammable solvent which combusts when dehydrated, producing nanoparticles which can be utilized further in ceramic materials fabrication, characterization, or performance testing. You will also have access to a pulsed laser deposition system for nanoscale thin film fabrication. Here, a laser ablates a solid target and transfers the target's stoichiometry to a heated substrate where it crystallizes as a thin solid film. You will also be able to spend time testing the electrochemical performance of your materials. I'll encourage you to construct and operate software and apparatus for automated electrical and chemical characterization. Here's just a basic setup I built with automated mass flow controllers, which flow gas through a water bubbler and into a tube furnace to hydrate ceramic pellets. Similar experimental setups will integrate digital signal generation and analysis hardware to perform electrochemistry of materials under carefully controlled thermodynamic conditions. I'm assuming some of my faculty colleagues have mentioned IMRI, which is currently one of the most advanced TEM labs in the world. There is an amazing collection of tools representing the state-of-the-art in aberration-corrected and cryogenic transmission electron microscopy. On this basis alone, and yes, I am absolutely biased about this, I would encourage you to consider getting involved in research which employs these tools even tangentially. The signals coming from these tools are truly at the forefront of our experimental and theoretical understanding of the physical and natural world. I will use these microscopes extensively in my research, so you'll have hands-on training and become regular users of these incredibly powerful characterization tools. As an IMRI user, you will produce electron microscopy data of nearly unmatched quality, like this high-speed video of atomic motion at the surface of an oxide exposed to reactive gas. Such dynamic data, which can be obtained while exposing materials to external stimuli, such as temperature, reactive gases or chemicals, or an electric field, are incredibly valuable for explaining the properties of these materials. I have also been active in outreach activities since I was an undergraduate student, and strongly value engagement with the community to convey our work generally. I think outreach activities are beneficial for developing communication and organizational skills, and can of course help to inspire the next generation of scientists and engineers. I've found strategic community outreach to be a fun, rewarding, and effective way to bring science and engineering concepts to audiences who may not traditionally be encouraged to explore STEM fields. For an example from my own work, I recently developed a short conference for students, postdocs, and early career professionals in microscopy and microanalysis. At UCI, I plan to develop local community outreach activities related to microscopy, and this summer I obtained an SEM which I plan to both modify and use to develop a microscopy teaching and outreach lab. As the first students in my lab, you'll receive hands-on mentoring with a commitment to a high level of productivity. Because this is a new and small lab, you will have exclusive access to brand new lab equipment. I am a strong proponent of undergraduate involvement in research, which will give you the opportunity to develop mentoring skills as well. Like I said, I've been active in outreach and will be an active proponent of community and professional outreach opportunities for my students. You will gain many transferable skills that you can use after grad school in industry or academia. Because we take a comprehensive approach to material science, you'll learn synthesis, chemical and physical characterization, coding, and writing. Central to these new skills will be electron microscopy, which will open up many employment avenues in many sectors. As part of your TEM training, I will send you to the Arizona State University Winter School on Electron Microscopy, which is a wonderful workshop where the world's preeminent microscopists have taught and/or attended as students. You will be encouraged to attend domestic and international conferences, which are critical opportunities to explore your scientific community, network with peers and professionals, and present your work. I typically attend meetings such as Microscopy and Microanalysis, Materials Research Society, the International Conference on Solid-State Ionics, the Gordon Research Conference, and the International Microscopy Congress. These meetings are valuable to students' education and professional development, and excellent opportunities to fundraise and win accolades for your hard work. I hope this presentation has piqued your interest in the microscopic world around you, and has inspired you to consider joining my lab. I am looking for 2 experimental students who are interested in materials for electrochemical energy conversion and storage, as well as transmission electron microscopy. If you join, you will apply a comprehensive approach to material science and development, and will learn many transferable skills which you can use beyond graduate school. As the first students in my lab, you will play an integral part in establishing the lab, and will have exclusive access to many brand new pieces of equipment. I wish each of you the best in graduate school and beyond, and I look forward to meeting you all in the spring.